In this video, we will demonstrate how our iTrace infrastructure works. This work is a collaboration between Youngstown State University and Kent State University. Software developers not only work with multiple source code files, but each of these files typically is comprised of thousands of lines of code. While reading and debugging code, it is not uncommon for developers to constantly flip through multiple files. Current state-of-the-art eye tracking software works well on fixed stimuli, such as images, but does not support tracking of developer gazes on these semantically and syntactically rich artifacts. Here you see some fixations on source code and a UML class diagram. Since source code files are quite large, we cannot feasibly draw areas of interest around each element to map gaze data to these regions. Clearly, we need a better solution. iTrace is our eye tracking infrastructure that enables conducting large-scale studies with software developers using various types of artifacts, such as source code. It reduces the time needed to set up and conduct an eye tracking study on software artifacts. Once connected to a tracker and after a quick calibration, the developer is free to work within their development environment while iTrace captures gazes as they are performing a task. These gazes will be mapped to specific source code elements via a post-processing module. iTrace is also designed with the goal of supporting additional eye trackers. The basic architecture for iTrace uses a central core application dedicated to setting up a study session and interacting with any attached eye trackers. Plugins are developed for specific development environments and communicate with the core to receive gaze point information. All gaze points are mapped to text or interface elements within the IDE and recorded during the study. Let's take a look at using the iTrace core. Suppose we want to start an eye tracking study. Let's start by clicking Session Setup. Here we can see that we have a few fields to help identify what our study is, who is running it, the ID of our participant, and the root directory where we will store the data for this session. This drop-down list shows all available trackers we have connected to our system. We are going to select the Tobii Eye Tracker. Now that we have selected an eye tracker, we need to calibrate the tracker. 9 different data points are used for calibration, and they are presented in a random ordering each time the calibration process is run. Calibration data will also be saved in the session data folder for review later. At this point, we have configured everything to start our session and could begin tracking, but to collect data associated with our IDE, we will need to connect one of our plugins to the core. Let's take a look at the plugins in action. With our plugin open, let's connect it to the core. For demonstration purposes, we will also enable an on-screen reticle provided by the plugin to show our gazes. Now that the plugin and the core are connected, we can begin tracking with the core. To end our session, we click the Stop Tracker button on the core. During plugin development, we have strived to maintain feature parity between the platforms. Similar to the plugin for Visual Studio, we can connect the plugin for the Eclipse IDE to the core. To demonstrate where we are looking during tracking, we can enable the gaze cursor just like we did for Visual Studio. Here we are using the open source project JHotDraw. We can see from the file browser on the left that this project is comprised of many files. iTrace is capable of handling scrolling and switching between these files while maintaining the context of what element is being looked at. When a session is finished, the core and plugin will both produce a set of recorded data about the study in XML format. The response records are joined by the session time field in each gaze response record. For optimal performance, we are not using real-time AST information derived from the IDE. Instead, we convert the source code into the SourceML format to provide AST information. This occurs as part of a post-processing phase where source code is converted to SourceML and together with gaze data is mapped to semantically meaningful elements via this automated toolchain. Finally, we have the option of running various fixation filters to generate fixations. The generated data can then be used towards some functional goal, such as determining navigation behavior. If you would like to learn more about iTrace and SourceML, please visit the link shown here for more information. Thank you for watching this demonstration.